Hello and good day everyone. In this video, we will be solving for the axial, shear, and moment diagram of a statically determinate frame. So the frame that we will now analyze would now be this frame here. So once again, the frame that we will be analyzing will consist of a lateral point load acting horizontally, and then a gravity load which is uniformly distributed and it would now act vertically downwards. So also in this frame, we would now be having two support conditions, namely hinge and then roller. Okay, and for the requirement for this problem is that we are now to determine the support reactions, the axial force diagram, the shear diagram, and then the moment diagram. So first things first, let us now solve for the first one, which is the support reactions. And in order for us to solve for the support reactions, is that we will be converting these supports here into their respective component forces. So as you know that for a hinge, it would now be having two components. Namely, we would be having the vertical component and then the horizontal component. And as for a roller support, in this case here, we would now just have one support condition or one support restraint, and that would become vertical. Okay, so for the forces for the hinges, or for the hinge I should say, I will name the horizontal force or the horizontal component as A sub H, and then for the vertical component I will be naming it as A sub V. And as for the vertical reaction at D, instead of us writing, let's say, dv, I would rather make use of rd, since for the resultant or for the reaction at d, it only has one component. Okay, so if you would be getting the resultant of that support, that is basically rd. So in this case, dv and rd would just be the same, and from that I would be making use of rd. Okay, so in that comparison or in that logic, for hinges, for this hinge, it really only has one support condition, and it is actually slanted in this manner. Okay, so as for the values of AH and AV, those are just a component of the resulting support force. Okay, but for the simplification of our solution, let us just have AH and then AV for the support conditions for the hinge at A. Okay, so in solving for the support conditions, let us now get the summation of forces horizontal, and I will be arbitrarily choosing a sign convention of to the right positive. And from that, as you can see here, that we have a horizontal force here to the right, and that is now 80, so 80. And then a horizontal force to the left of AH, but since it is to the left, I will be assigning it as negative. Okay, so solving for the value of AH, I think by common sense or by inspection, you can now say that the value of AH is equal to positive 80 kilonewtons. Okay, so proceeding, let us now solve for the, let's say, moment, or let's say, let us now solve for the reaction at D, and that is RD, and from that, I would now be getting the moment at A. So I will be getting the moment at A in order for me to cancel the value of AV. Because as you know that for a moment is equal to force times distance, or force times lever arm. And if you would be getting the moment about this point, the lever arm between this point and this force is actually equal to 0. And from that, guys, I would now just be having one unknown later on. Okay, so in my sign convention, I will be using clockwise positive. Okay, and from that, guys, from this point here, so from this point here, let us now enumerate all of the forces that would cause rotation, once again about this point. So we have this 80 kilonewton load here, so 80 kilonewtons. And since we are to deal with moments, we would be multiplying it by the lever arm. And when we say lever arm, that is the perpendicular distance from the point up until the force. So the perpendicular distance from this force up until this point, that is 3 meters. So once again, we would be multiplying this by 3 meters. So as per the sign convention, since I arbitrarily chosen clockwise positive, as you can see that, let's say that you will be holding this point. This force has a tendency to rotate this point in a clockwise direction. So it would now rotate about this manner. So since it is clockwise, meaning that it must be positive, since in our sign convention, clockwise positive. Okay, so proceeding, we also have this force here. But take note that in this force, it is uniformly distributed. It would be better, actually, for you to solve for the resultant force first. Okay? So for the resultant force, that is equal to the uniformly distributed load times the distance. Okay? So times 5 meters. And take note that this force here would be acting at the centroid of the rectangle. And when we see centroid of the rectangle, it is just at the midspan. Okay, so there. And from that, guys, since this force would cause a clockwise rotation about this point, it is still positive. So that is positive 5 times 5. But take note, guys, that this is just the force. Um, in in our solution here, we must solve for the moment first. Okay, so once again, moment is equal to force times lever arm, and the lever arm here is equal to the half of 5, which is 2.5. Okay, so what else do we have here? We still have the value of RD, and RD is actually pointing upwards in my assumption. And if that is upwards, if you would be analyzing this point, the tendency of RD is that it would rotate point A in a counterclockwise direction. So as you can see, it would now be like this, counterclockwise. So from that, RD must now be equal to a negative value times, of course, the lever arm of 5 meters. So solving for the value of RD, looking at the calculator to the left. So let's say that I will be transposing RD to the other side. So that is now equal to 80 times 3 plus 5 times 5 times 2.5. So divided by 5. So that is now equal to 60.5. So if you do not want to, let's say, solve it that way, you could also use shift solve feature in your calculator. So once again, RD is now equal to 60.5 kilonewtons. Okay, so solving for the next one. So solving for, let's say, call this the support reaction for AV, since you already have the value for AH and RD. We could just get the summation of forces vertical. So if you want to get the moment about this point, so feel free to do so. You would still be arriving at the same answer. But for the simplification of our solution, let us just get the summation of forces vertical equal to 0. And in my sign conventions, or sign convention, I should say, upwards positive. So we have AV, of course, AV, which is positive. Then this force here, that is 5 times 5, plus RD. And since in our RD, we have solved for it as 60.5, so plus 60.5. Okay, so this is now equal to 0. Then solving for the value of AV, looking at the calculator. So if I am to transpose 5 times 5 to the other side, so that is 5 times 5. And if I would be transposing 60.5 to the other side, that is negative 60.5. So from that, the answer here is negative 35.5. So this value here, or this sign here, indicates that I wrongly assumed the direction. So as you can remember earlier, that I have assumed the direction for AV to be upwards. So this negative sign here indicates that that is actually incorrect. Rather, it must be downwards. Okay? So notice this arrow here, which was originally pointing upwards. So again, that is incorrect because this is the correct direction. So I will be reversing it. So from that, guys, for the value of AV, it must be pointing downwards. AH is to the left, RD is upwards. Okay, so in the analysis of our frames, we would be analyzing it in this manner. So I will be analyzing this beam here upwards, and then for this beam here to the right, and for this beam here downwards. Okay, so take note, downwards, not upwards, downwards. So why would I be analyzing it that way? Because a frame is basically a beam, I should say. So once again, A frame is basically a beam that was bent at these joints here in such a way that it would now be looking like this. Okay, so say that we are to do the opposite. If we are to bend this frame in such a way that it would now become a straight beam, it would now look like this. Okay, so once again, from this frame, it would now be looking like this if we would be bending the whole frame in such a way that it would be straight. So notice this arrows here. So this arrow here is upwards, this arrow here is to the right, and this arrow here is downwards. And if we would be stretching it in this manner, all of those arrows would now be pointing to the right. If you can remember from before, when you have solved for the shear and moment diagrams of a beam, we analyze it from left to right. So same is true with frames. We analyze it from left to right, but as you know that some of the beams here are now oriented vertically, so this is now our flow. Or in other words, it is, or the analysis will now be done in a clockwise direction. Okay, so if you're wondering if when I say that this is a beam, and let's say that if you would be having an argument saying that that is not a beam, rather that is a column, so yes, you are correct. However, guys, a column is basically a vertical beam. Okay, so proceeding. So let us now go to the next slide here. So in order for us to analyze the beams separately, or let's say if you want to solve for the moment and shear diagrams for the whole frame, the best thing that we should do, or the next thing that we would be doing, is for us to separate all of these elements into, of course, there's a separate entities. However, take note here, guys, that earlier when they were still connected, so of course they would be connected in this point and in this point, and their manner of connection, since it was not indicated in the problem that it is neither internal pin or internal roller, we are to assume that this connection is fixed. Okay, so they are fixed, connected at these joints. And from that, guys, if we are to separate these beams, so since they are separated, take note that earlier this joint here and this joint here are fixed, connected. And when we say fixed, we would now be having three component restraints, namely the horizontal, the vertical, and then the moment. Okay, so for our nomenclature, as you can see here, we have VBA, NBA, and then MBA. Okay, so VBA stands for shear. V stands for shear. N stands for normal force or axial force. M stands for moment. So for VBA, as you can see that V, this is shear. And if you would be looking at this force here, it is actually parallel to the cross-section of this column. Okay, cross-section. So parallel and from that shear. And this force here, this force is acting perpendicular to the cross-section of this column. Thus, NBA or normal force. Okay. So for VBA, BA stands for, this is the shear V at joint B on beam BA. Okay? So suppose that you are now to solve for the shear here. For example, the shear here is VAB. Okay? So since shear at joint A for beam AB. So since in this location, this is joint B, so VBA. So same is true with NBA and then MBA. Okay, so what about for the other beams? So for this beam here, we would also have a horizontal force, a vertical force, and then a moment. But take note, guys, earlier the shear BA was horizontal, but in this case here, the horizontal there is the normal force. Since this force is acting perpendicular to the cross-section here, thus this is the normal force or the axial force. So we have the normal force, the shear force, and then a moment. And as for the other side, we have NCB. So take note the difference between NBC and NCB as further naming. Okay, so NCB stands for, this is the normal force at joint C for beam CB. Okay, so Aside from that, we also have the shear at CB and then the moment at CB. And then for this one here, we have a shear CD, a normal CD, and then a moment at CD. Okay, so let us now reconnect this. Let's say, we would be reconnecting this beam to this beam together with their forces. So as you can see, it would now look like this. And then suppose that we will now be getting, or we would now be solving via method of joint. So let's say that you would be getting this particular joint here. And from that, guys, let's say that we are now to apply the equations for static equilibrium, namely summation of forces horizontal, summation of forces vertical, and summation at moment. Again, at this joint only. So for summation of forces horizontal, we could now say here that NBC minus VBA is equal to 0. And from that, we can now say that NBC is equal to VBA. Or just by visual inspection, guys. So by visual inspection, as you can see, that the value for NBC is equal to VBA, since they are the only horizontal forces present in that joint. And we could now say that NBA is equal to VBC, and we could also say that the MBA is equal to MBC. Okay, so once again, NBC is equal to VBA, NBA is equal to VBC, and that MBA is equal to MBC. So meaning the horizontal component of the other beam is just the component of the other beam and vice versa. So if we are to separate them once again, guys, in our analysis earlier, we could now say that VBA is equal to VBC. It is just that they are opposite. If NBA is upwards, then we could now say that VBC is downwards and vice versa. Okay? And from that, guys, the value for VBA, that is equal to the value of NBC. It is just that their directions would be opposite, as well as the moment at BA is equal to the moment at BC. It is just that one is counterclockwise and the other is clockwise. Okay, so we would be making use of that principle later on. So let us first analyze the first beam, or the column, as you would say, in this portion. So let us now solve for the values of VBA, NBA, and MBA. So let us get the summation of forces horizontal first. So summation of forces horizontal, and my sign convention to the right positive. So from that, guys, you would now be having a horizontal force AH, which is to the left. So negative AH. And then you also have a value of 80, which is to the right. So positive 80. So this now equal to, that is not yet equal to 0. So another horizontal force that is present in this beam is VBA. Okay? So minus VBA. So since I assumed that it is to the left. Okay? So solving for that, so that is equal to 0, then substituting the value of AH. So the value of AH, this is 80. And negative 80 plus 80, that is equal to 0. So from that, guys, we could now say that VBA is equal to 0. Okay, so once again, this is now equal to 0. So for the next one, summation of forces vertical, that is equal to 0, let's say upwards positive. So we have here a 35.5 kilonewton force acting vertically downwards. So that is now equal to negative 35.5. And then I assumed here that NBA is upwards. So for upwards NBA, that is plus NBA. So we do not have any other vertical loadings in this beam. So this is now equal to 0. And from that, we could now say that NBA is equal to 35.5 kilonewtons. Okay, so that is for VBA and NBA. So what about for MBA? So for the value of MBA, we would now be getting the moment about that portion, or this point. So in my sign convention, clockwise positive. And from that, guys, so about this point, let us analyze, or let us pinpoint, or let us enumerate all of the forces that would cause rotation. So namely, 80 kilonewtons. So 80 kilonewtons, and as you can see that its rotation would now rotate in a clockwise direction. And if it is clockwise, meaning that it is positive, times the lever arm of 3 times, 3 plus 3, that is times 6, minus 80. So this force here times the lever arm, 3 meters. So y minus, because as you can see, guys, that let's say that this is the force, its direction is to the right. About this point, it would cause a counterclockwise direction, thus negative. Okay, so another thing about this point, this moment MBA would also cause rotation. And as you can see that in my assumption, I assumed it to be counterclockwise. Thus, it must be negative MBA. So this is now equal to 0. And from that, solving for MBA, looking at the calculator to my, below me. So if I am to, let's say, transpose MBA to the other side, so feel free to use shift solve if you want. So this is now 80 times 6 minus 80 times 3. Oops, sorry. So this is now 80 times 6 minus 80 times 3. So the answer here is, so for the value for MA, that is now, or MBA, that is now 240 kilonewton meter. Okay, so take note of these answers. So let us now put them here. So for the value for VBA, that is equal to 0. For the value for NBA, that is equal to 35.5. And for the value of MBA, that is equal to 240. So using our principle earlier, that stating that VBA here is equal to NBC here. So from that, since VBA is equal to 0, we could now say that NBC is equal to 0. So as for NBA, so NBA, the vertical force here is just equal to the vertical force here. It is just that their directions would now be the opposite of each other. So from that, if NBA is equal to 35.5, we could now say that VBC is 35.5 downwards. So if this is upwards, this must be downwards. Okay, so for MBA, so since it is 240 kilonewton meter counterclockwise, for moment at BC, it must be 240 kilonewton meter, but it is now clockwise. Okay, so proceeding to the next beam, which is this beam here. Once again, NBC is equal to 0, VBC is equal to 35.5, MBC is equal to 240. Okay, so solving for these values here, since you already know these values, so if you would be getting the summation of forces horizontal, since NBC is equal to 0, we could also conclude that NCB is now equal to 0. So if you have trust issues, solve for it yourselves, you would still be arriving at the same answer. Okay? So for the value for VCB, so what about for the value for VCB? So we do not know what the value of VCB is yet. And we still do not know what the value of MCB is, once again, yet. So once again, if you would be getting the summation of forces horizontal, you would be arriving at an answer of NCB is equal to 0. And if we are to get the summation of forces vertical is equal to 0, upwards positive. So let us now enumerate from left to right all of the vertical forces. So we have here VBC. Okay, so shear at BC, and that is once again equal to 35.5. And it is downwards. Okay, so thus negative 35.5. So what else, or what vertical forces is present in this figure? So we still have the value for the uniformly distributed load, but take note that we must solve for its what do you call this, resultant first. So the resultant for that force is equal to negative 5 kilonewton per meter times 5 meters. Okay, so this is now the resultant. So do we still have other vertical forces present here? So yes, we still have the value for VCB. And in my analysis here, I assumed it to be downward. So I may be incorrect, I may be correct. So again, this is just an assumption. If I would be having a negative answer, it is just that my assumption is incorrect. So minus VCB, so that is now equal to 0. So solving for VCB, looking at the calculator to your left, if I am to transpose VCB to the other side, so that is now negative 35.5 minus 5 times 5. So the answer is negative 60.5. So again, the negative value here indicates that I have wrongly assumed the direction. So in my initial assumption, that is downwards positive. So meaning that the value for VCB is 60.5 kilonewtons, but it is now upwards. Okay, so take note that it must be upwards. So from that, guys, let us reverse VCB later. So for now, let us solve for MCB in order for us to proceed. So in order for us to solve for MCB, we would be getting the moment about this point. So getting the moment about that point, that is summation of moment at C is equal to 0, clockwise positive. So we have, so what causes rotation about this point? So first things first, if we would be going from left to right, we have here the moment BC, okay? So this would also cause rotation about this point. So for MBC, as you can see that it is clockwise. So positive. Okay, so what else? We also have the value for VBC. And as you can see for the value of VBC, that is now downwards and that would cause a counterclockwise direction. So minus VBC. But take note, uh, we must multiply this by the lever arm, and that is 5 meters. So VBC times 5 minus 5. So why minus? Because as you can see that this 5 kilonewton per meter force here is pointing downwards, and that would cause a counterclockwise direction, thus negative. But we must get the resultant of this first by multiplying it by the total length of 5. But take note that this is just the force. This is just the force. We must multiply this by the lever arm of half of 5. So this is now the lever arm, which is 2.5. So multiplying it by 2.5, then minus CB. So since in my assumption here, MCB is counterclockwise. So again, this is just an assumption. I may be incorrect, but you feel free to assume that this is clockwise. So meaning that if your answer later on is positive, it means that you have correctly assumed the direction. If your answer is negative, then meaning that you have incorrectly assumed the direction. So from that, this is now equal to 0. Then solving for the value of MCB, I should say. So substituting all known values, this is now 240 minus 35.5 times 5 minus 5 times 5 times 2.5 minus MCV, that is equal to 0. So looking once again to the calculator to your left, so that is now equal to 240 minus 35.5 times 5 minus 5 times 5 times 2.5. The answer there is equal to 0. Okay, so MCB is now equal to 0. So from that, summarizing our answers. So this is now our answers. So NCB is equal to 0. VCB is equal to 60.5 upwards. MCB is equal to 0. Okay? So in order for us not to get overwhelmed by the figure, I think it would be better if we would just be removing all of the forces in a magnitude of 0. So NBC is equal to 0. So meaning if this is NBC, that is equal to 0. So let us just remove that. Okay? So as for the other side, NCB and MCB are 0. Thus, let us just remove MCB and let us remove MCB. So this is basically the free body diagram of the beam at the top. Okay, so proceeding for the final element in our frame, let us now analyze this one here. So, okay, here. So since the value for MCB is 0, we only have VCB. I think it would be better if you would just be removing MCD and VCD later on. But let us do it theoretically. Okay. So for the value of VCD, that is already automatically equal to 0, because if you would be getting the summation of forces horizontal, that is 0. And once again, in our analysis a while ago, whatever the value is here, it would now be having the same value as this one here. It is just that they are different in direction. But since this is 0, this is also 0. So since NCB is equal to 0, VCD is also equal to 0. But what about for NCD? Okay, so for the value for VCB, we have here a value of 60.5 upwards. That is for VCB. For NCD, we would now be having the same magnitude. It is just that it would now be pointing downwards. Okay, so for the moment at CD, so MCD, that is equal to the moment MCB. It is just that they differ in direction, but coincidentally speaking, MCB is equal to 0. Thus, MCD is also equal to 0. Okay, so proceeding here. So let us just remove those. And from that, guys, as you can see, the only one remaining here is the value for NCD, and that is equal to 60.5. Okay, so since we do not have the value for VCD and MCD, if you are to analyze this beam here, I think all of the necessary information are already there. So we do not need to solve for the summation forces horizontal, vertical, and then moment about any point here since there are no unknown values. Okay, so proceeding once again. So since we already know all of these forces, what we will be doing next is for us to draw the axial, shear, and moment diagrams for each of these elements. So for the first element, which is this column, so let us first draw the axial force diagram. Suppose that this is the beam. So for the axial force diagram, our sign convention here is tension positive and then compression negative. Or suppose that this is a beam, or let's say if you are to tilt your head in such a way that this is, let's say, the right, this is the left, and this is the right side. Okay, so we could also say that for the axial force diagram, summation of forces horizontal is equal to sorry, let me just erase this. So once again, summation of forces horizontal to the left positive if you do not want to make use of this sign convention. Okay, so the value for AV, as you can see, is 35.5 kilonewtons downwards, and as you can see that for that one, it is tension. So meaning it must be positive. Okay? And if you are to use this sign convention here, tilt your head in such a way that this is left and this is right. If you are to get summation of forces to the left, positive. So if you are to tilt your head, this value here is to the left. Okay? Though if your head is upright, that is downwards, but if you would be tilting it in the direction of that beam in this manner, this would now be to the left. So if that is to the left, that is 35.5 to the left, that is again positive. And from that, guys, this is now our axial diagram. Okay, so as you can see that from this point to this point, we only have one axial force. And if we are now to look at this NBA, so for NBA, that is 35.5 kilonewtons upwards. And once again, if you would be tilting your head, that is to the right, okay? So since our sign convention here is to the left positive, just for the axial force diagram. So from this point, you would now be going, or let's say if this is 35.5, 35.5 minus 35.5, that is now equal to 0. Okay? So that is for the axial diagram. So for the shear diagram, so suppose that this is now the shear force diagram. At this point, the beam is being subjected by 80 kilonewtons to the left. Thus, we will be making, or we will be moving 80 kilonewtons to the left here. Okay? And then from this point to this point, we do not have any lateral loads. So meaning, we would just be getting a vertical here. And then as you can see here, we would be moving 80 kilonewtons to the left. So from this point of 80, we will be moving 80 kilonewtons to the right, I should say. And this is now equal to 0. And from that, guys, from this point to this point, we do not have any lateral load. And as you can see that VBA is equal to 0. Thus, to confirm, VBA is equal to 0. Okay? So as for the moment diagram, guys, you could cut any section you want. But if you would be making use of area method, for the moment diagram, so since this support here is a pin support, it does not have any moment restraint, meaning that the moment diagram will start at 0. So moment start at 0 plus the area of the shear diagram here. Okay, so as you can see here, this here is 3 meters. So this is 3 meters. So the area of this shear diagram is 80 times 3. So looking at the calculator once again. So 80 times 3, that is equal to 240. So meaning that from this point up until this point, so this is 240, okay? And you will be connecting that. So let me just erase this first. So again, 240 kilonewton meter. So if that is 240 kilonewton meter, you would just be connecting them with a straight line since this is a plane or this is uniformly distributed. So this is now a straight line, okay? So from this point up until this point, straight line. Then from this point to this point, as you can see that we do not have any area here. So plus 0. So 240 plus 0, that is equal to 240. Thus, it will not change. Okay? But take note, guys, that from this point, so at this particular point here, so if you can remember our lecture from beams, that for our sign convention for moment diagrams, that is summation moment, clockwise, positive. But at this particular point, we have a moment of a counterclockwise moment, which is negative. And what is this value? For the value for MBA, that is equal to 240 kilonewton meter. So meaning, if this is 240 here, we would be subtracting. So we would be subtracting 240 from 240. Once again, if this is 240 here, and since we have a counterclockwise moment of 240 that would be moving to the left, so from that, 240 minus 240, that is now equal to 0. Thus, 0. Okay, so proceeding to the next beam. So by the way, this is now the axial shear and moment diagram for column 1 or beam number 1. So for the next beam here, so for the axial force diagram, as you can see, NBC is equal to 0 and NCB is equal to 0. So basically, this is already our axial force diagram, which is 0 throughout. So for the shear force diagram, as you can see here, that for VBC, we would be going downwards by 35.5, thus negative 35.5. Okay? So from this point, negative 35.5, if we would be moving from left to right, we have a uniformly distributed load of 5 kilonewton per meter. So meaning that for every meter that will be covered in the beam, there is a 1 kilonewton load acting downwards. Or sorry, 5 kilonewton load acting downwards. So 5 kilonewton per meter. So meaning that in order for us to get the shear at this particular point, that is equal to negative 35.5. And then in this force here, in this uniform load here, it means that it is actually going downwards here. So since this 5 kilonewton per meter is pointing downwards, if that makes sense. So in order for us to know the next point here, that is equal to negative 35.5 minus 5 times 5, or minus this area here. Okay? So for that area, so looking at the calculator, that is the last point, which is negative 35.5, minus the area, 5 times 5. So from that, the answer here is negative 60.5. So negative 60.5. Okay? And as you can see that at this portion, we have a 60.5 kilonewton load directed upwards. So from that, from this point, it would now travel 60.5 kilonewton upwards. So from that, guys, negative 60.5 plus 60.5, that is now equal to 0. So from that, our shear diagram closes. Okay, so for the moment diagram, guys, take note that for our assumption here, not assumption, but in our solution, I should say, this here is fixed support. So this here is a fixed support, meaning that it has moment. So contrary to having a pin or roller support that for those joints, we will be starting at 0. This time, for our moment diagram, we will not start at 0 because we have a moment here. So again, our sign convention is clockwise positive. And since this moment here is clockwise, meaning the value of the moment here is positive. So MBC, that is 240. So positive 240, positive 240. Okay, so we would be starting at positive 240. Okay, so for the next joint, which is this joint here, we would be getting 240 kilonewton meter minus this area here. So this area here, so y minus because this area here is below the positive line or negative. So since this value here is negative, okay? So since it is below the 0, 0 line. So there are plenty of ways on solving for the area here. So one method is by dividing this into two triangles. So let's say that this is area 1 and this is area 2. You could be doing it that way. Or you could also do it in such a way that you would be dividing this trapezoid in this manner, whereas this is area 1 and this is area 2. And just for the sake of this discussion, I would rather get the area of the full trapezoid. So let's say that this is now the area itself. So the area of a trapezoid, if you can remember, so area is basically equal to, so area of a trapezoid, that is equal to 1/2 or the averages are the average of the heights times the length. Okay, so regardless of what method you will be choosing, your answer should be still be the same. So from that, guys, just looking at the calculator, so the area for the trapezoid, that is equal to 1/2, so 1/2 or 0.5 times height 1, that is negative 35.5, minus 60.5 or negative 35.5 plus negative 60.5, you could do it that way, times, call this times the length of 5 meters. So negative 240. Okay? So meaning that the area here is negative 240. So from that, from 240 minus 240, that is equal to 0. So this is now your next point. So take note, guys, that we would not just connect this with a straight line because the shear force varies. Rather, it would now be curved. But if you are now wondering if the curve is like this or if the curve is like this, your basis for the direction of the curve would now be dependent upon the values for shear. So we have this value here and this value here. As you can see that in this value here, it is actually downwards. But the value of this part, so let me just erase in order for us to have a systematic drawing. As you can see that this part of the beam has a higher shear, a higher negative shear as compared with this beam here. It means that the slope at this point here, would now be greater than the one at this point. Okay, so meaning that it would now slope in this direction. So if you want to review on that, feel free to watch our previous video on beams. Okay, so from that, guys, the moment diagram would now look like this. So that is for the beam at the top. So for this beam, okay, so for the axial diagram, let's say that we are to analyze it in this manner, whereas this is left and this is right. So if you are to get the summation of forces horizontal to the left positive, NCD, if to the left positive, this is acting towards the right, meaning that this is now negative, since Again, this is downward, so this is negative. So, negative. So, if you're wondering, sabi mo, sir, downwards. Di naman downwards, to the left yan. Once again, tilt your head in such a way that this is left and this is right because our manner of analysis is from this point to this point. Okay? So, assume that you will be tilting your head onto that direction. Okay? So, that is 60.5. Then, so this is now the axial force diagram. So, negative 60.5, where did that come from? Again, our sign convention, tension, positive, compression, negative. Okay, so proceeding, what about for the shear force diagram? If you are to look closely here, we do not have any shear force. And as for the moment diagram, as you can see, no rotation is happening on this beam. So that is now the shear and force diagrams for this particular column. So proceeding, guys, let's say that this is now our whole structure. If we are now to compile the moment diagrams, this is now the moment diagram of the first beam. This is now the moment diagram of the second beam. And as you can see that we do not have any moments here. So basically, for the moment diagram of the whole beam, that is now what it would look like. So there.